Today we'll very briefly summarize the integration strategies we've looked at so far. We'll discuss roughly how to approximate a good strategy to use to compute an integral. As we've seen, simplifying the integrand if possible is a good idea, either through algebraic manipulation or using trig identities to reduce or rewrite the integrand. If you're still not sure what to do, think about a u substitution or some other kind of substitution. If you can, a u substitution is generally quicker, so that's a good thing to look for first. If not, you can think about some integral formulas, if any apply, like the one we mentioned for tangent or secant, or the other ones that you may be familiar with from Calc 1. Then, if not, right, think about the form, and this is sort of where we get to the strategies we've discussed here. Right? If there are trig functions involved in the integral, try using trig identities to rewrite. Try using the trig integration techniques that we discussed. If you see a rational function, then two things should come to mind. Try long division if needed, if the numerator has a higher or the same power as the denominator. If not, try partial fractions. If you see a radical somewhere in your integral, then a trig substitution, as we discussed, is a good idea. We mentioned rationalizing substitutions pretty briefly in the partial fractions at the end of the partial fractions video. That's kind of a good strategy to use in some cases too with radicals. Lastly, if you see multiple types of different functions, then integration by parts is a good plan. If you try something and it doesn't work, try something else, right? Keep trying. It's okay if the thing you think first doesn't exactly pan out. Sometimes, in fact, you learn more from trying something that doesn't work than if you try something that does. So that's okay if it doesn't work out. Try a different method. Try something else. Sometimes you may need to, as you've probably seen even a little bit already, you may need to combine multiple of these techniques that we look at together in order to deal with some things. Here's a table of integrals that you do need to know as you continue throughout. Most of these you probably know already. You probably discussed these in Calc 1 before. But you definitely want to be familiar with these 13 different integrals as you approach more complicated ones. If you can recognize these and know that you don't have to worry too much about how to solve them, then you're in good shape as far as once you've gotten to this point from those more complicated ones. A last thought, can we integrate all continuous functions? You want to say yes, but no, we can't. There are lots, and we'll investigate lots of different types of functions that we can't integrate, algebraically anyway. The ones we have looked at so far are what we call elementary functions, things like polynomials, rationals, power functions, including exponential functions, log functions, trig and inverse trig. We don't do much with these, but hyperbolic and inverse hyperbolic functions, and then functions you get by combining a bunch of those different types together. So we've seen a lot of those, and not even all of those can be integrated, but some of them can. In fact, though, a majority of these elementary functions that we've been working with so far don't even have elementary antiderivatives or integrals. You can probably think of some. E to the negative x squared is a good example that we'll look at several cases later in the semester. But think about some other ones that might not work, and this is sort of a preview into some numerical integration that we'll look at. But the idea is that no, we certainly can't integrate all continuous functions or even all elementary functions that we look at. So once again, if you try a bunch of things, don't panic. It may be that that particular integral you're working with is not doable with these types of functions that we've studied. And so that's okay. We'll look at some more techniques to approach those soon.